computer actually, a big like coding computer, and I called it Magneto. So yeah, okay. So most of my research, it's going to be a balance of being really vague and detailed, and it's probably going to fail at both of them. So there's not going to be that much math. So I just want to give you kind of a broad idea of what I do, and I picked some specific topic that hopefully is interesting that I'll talk about in the middle there, and then I'll show you lots of pretty movies and things like that. So most of my research is on scientific computing, and applications have been complex fluids and magnetohydrodynamics, which I'll explain what that is soon enough. But real brief, I work with a lot of people, and maybe some of you guys, hopefully in the future, but all over the world, and so a lot of people work on these projects. And the great thing about scientific computing is that you can get into a lot of fields, from the application side, from the mathematics side, from the computer science side, so you can get to meet a lot of people. So I'll give you a brief introduction of scientific computing. Apologize to the guys that saw this already, but this is even briefer than before. But why is simulation important now? Well, it's becoming like the third prong or whatever three thing that you like in scientific studies. So normally you had theory and experiment. Well, now you're getting experiments that maybe are intractable or really expensive to do. So it's a lot easier to simulate that on a computer first before you invest billions of dollars in an experiment. It's also being useful for validating theories and things like that. And all these processes feed back on each other. And that is a real quote from Yogi Berra. Okay, so back in 1965, co-founder of Intel, Gordon Moore, made the statement that the speed of a computer will double every 18 months, and he was pretty accurate over the last 50 years. It's actually more along the lines of every 2 years now, but this is since 1950 to 2000. These are like the fastest computers at the time, or at least the most efficient ones. And on the left here we got flops, so floating point operations per second, how many additions that computer do per second. And in 1950 it was on the order of 1,000, and now today we're even beyond this. So this is 1,000 billion teraflop, and then now we have 1,000, it's called a petaflop, 10 to the 15, yeah, 10 to the 6, 9, 12, 15 flops the computers can do per second, which is pretty fast. Now there is a slight, stop it. Conspiracy theory that, I'll start the sentence over. So, and by the way, please stop me and if you have questions or corrections, because but it actually makes my story better. So he said the number of transistors on a computer will double every 18 months. And that has been pretty accurate. But of course, the conspiracy theory is that Intel actually has the most advanced computers for the next 50 years, and they're just selling them at every 18 months just to keep up with this thing. Like maybe or maybe not. So what's going on? Well, here's the transistor counts over the last, again, 40 years, and they've been about doubling every 2 years or 18 months, somewhere in there. But in the most recent years, in the last 10 or so, while the number of transistors has been doubling, the CPU time has actually kind of flattened out. And what's going on there? Well, we're starting to reach physical limitations of these chips, like the chip size, how small can you actually get it for these things. I mean, you still have physical, they might be electrons, but they're still physical entities going across that so they have some limitations. The storing of memory is actually an issue that a lot of people don't talk about, how you're getting larger and larger data, how do you store it? And the other big thing is power. In order to run one of these giant machines, you need a lot of power. And if you want to keep doubling the speed every 2 years, eventually you're going to need reactors that can power a whole city just to power your computer. So we need more efficient ways of doing this. And yet, still, computers have been following Moore's law. And that's because of the introduction of things like parallel computing, multi-core machines. Like now in your laptop, you have like 4 cores in there doing things simultaneously. And we're helping keeping up, but still, those are reaching limitations. For instance, now with parallel computing, you have 2 chips doing simultaneous things, but then eventually they have to talk to each other. And if you have billions of processors, that's billions of conversations, and too much conversation doesn't get you anywhere sometimes. So what's really, in the most recent years, actually advancing the speed of computers is actually the mathematics. The numerical algorithms that are being used to solve equations that are going into these computers are what's been making this Moore's Law actually work. And if you look at Moore's Law from that point of view, for speed up of computations from some certain mathematical algorithms, you'll see that it's sometimes even beating Moore's Law. So these are examples of linear solvers solving AX equals B on a computer. The simplest thing would be a direct solver, Gaussian elimination, like we do in linear algebra class, row reduction. You get a computer to do that, it'll take you n cubed operations. But you can actually come up with more advanced things like banded Gaussian elimination that'll give you like order n squared. And then you have iterative methods that can go get you order n operations. So you have an n by n matrix, it'll take you n floating point operations to do it. Is that a question?
Yep. Yeah, what's your zero?
35 years ago from 2000. Good question. 1965, I guess. So this is when the introduction of these methods were. Well, probably, yeah, somewhere around 1960.
The Unix 0.
That's the year zero. Okay, and a more particular, a very specific application which I'm interested in, fusion energy simulations, you can look at the effective speed up of the simulations coming from just hardware, blue line, coming from mathematical algorithms, and coming from better physical models to approximate these systems, and where the speed up in the simulation time is actually coming from. So mathematics and better physics are actually greatly improving the speed up of computational simulations. And that's why we like it. So what is scientific computing model? Well, you get to be involved in all sorts of levels of this stuff. You want to model some physical phenomena, you have to come up with a physical model to describe this. You want to describe the weather, what are the processes going on. Then we want to break that down into a mathematical problem that we can actually look at and solve. And then if we want to put that on a computer, well, a computer doesn't like continuity, it likes discrete, bits, ones and zeros. So we have to come up with a discrete model to model that mathematical model. And then once you get that, some system, maybe an equation or something, you want to be able to solve it, so you have to come up with efficient solution algorithms. So there's a lot of numerical linear algebra goes on in there. And then of course you have to implement it. Computers are really, really fast, but they're really, really dumb. It will only do whatever you tell it to do, and they'll do whatever you tell it to do really fast. If you tell it to do the wrong thing, it will get the wrong answer pretty quickly. And then in the end, you get this answer. It's an answer to your solution algorithm, which should be an answer to your discrete model, which should be an answer to your mathematical model. How do you actually know what it is? You have to be able to visualize it, and this is a big field in computer science, which I hardly touched on in my career, but it's very important to be able to analyze this data. And then, of course, you want to verify and validate what you're doing. You get an answer to this discrete model. Does that really represent the answer to your mathematical model? And if so, is that answer to the mathematical model actually represent the physical thing? So if you have a well-posed physical system, you better have a well-posed mathematical system, and you better have a well-posed numerical system. And even if they're all well-posed, do they represent the same thing at every level? So you get to be involved in all these things, which is kind of neat. So most of my work has been probably in these three areas, looking at the mathematical model, trying to make a discrete model out of it, and then solving the system. Of course, I have to do a lot of coding and things like that. You can come up with one thing I learned, you can come up with a really awesome algorithm that's really fast, and then you implement it like an idiot, like I do most of the time, and it's really, really slow. There's a lot to be said for this area. So, what am I specifically looking at? What is my research focus? Well, numerical analysis for the solution of partial differential equations. So I'm looking at physical systems that are described by PDEs, and specifically ones that involve lots of spatial or time scales. So things like plasma physics, multi-phase fluids, atmospheric dynamics, particle transport. These are things that have lots of processes going on at different scales. So for instance, in a plasma, which is I'll get into a little bit more detail in a second, it's a charged fluid. So fluids, it moves on some macro scale, like slow moving waves and things like that, and you have to model that at some macro scale. But it's charged, so there's electrons and ions flying around close to the speed of light, and you want to resolve that behavior as well. So you need to resolve these things, so you need multi-level adaptive techniques that can actually resolve these skills efficiently with the given amount of resources. So what I want to do is solve these problems efficiently, meaning I want to get it accurate and represent the actual physical first principles, but also, I'll just throw them all out there, but also want it to be efficient. In other words, the amount of computational time that it takes to solve this problem should be small. I want to be able to solve this. It's no use for me predicting the weather for tomorrow really, really well when the answer comes out 10 days from now. Right? So you have to have this balance. Well, I can predict it for tomorrow. It won't be as good if I had more time, but at least we get it before tomorrow. So these are the things I look at. Being consistency with first principles, so you have to come up with a discrete model. Discretization methods are called, that are well posed. In other words, if you want to model something on a computer, the simulation better not blow up if the real thing did blow up. The solution would go to infinity, things like that. You want to use specific properties of each model, the discrete model, mathematical model, to make your solution algorithm faster. So you come up with robust, nonlinear, linear solvers. A lot of my research is multi-grid methods, which can obtain that, and adaptivity, which when I show you my results, I'll explain some of this in more detail. It's a little bit vague. And then, of course, we have to be mathematically rigorous, so we want to prove that the method I come up with is actually going to give me an accurate answer. It actually satisfies all the properties, the physical properties that I want, and is also going to be, say, order n operations, be efficient. And then again, you want to validate that what you're getting is what you really want. Okay, so that's the broad view of what I do. So I'll pick a random topic that I look at. And one thing I did at a postdoc at Penn State was my thesis was on magnetohydrodynamics and coming up with solution algorithms for that, which I'll explain in a second. And then when I went to Penn State, I worked with a guy named Chun Liu, whose expertise was in PDE analysis. And he had this philosophy, which this should be the standard philosophy, is that what is a PDE? I mean, it's made up mathematical construction to describe some physical behavior. Well, what is the physical behavior? What's controlling that? It's the forces or the energy that's all controlling what's going on. So what you should do is look at this PDE, where it comes from, which comes from some energy law. And when you go to your discrete model, you should always keep this in mind. So most physical processes are determined by some energy law, where the change in conservative energy is going to be equal to some dissipation. You have no dissipation, energy is conserved, and the time change will be zero. You have dissipation, like heat loss, friction, things like that, your conservative energy will decrease. So we look at that, and this is what drives all the physics, and this is how you can derive all the forces using some variational calculus. So the variation in conservative energy with respect to the domain, this will give you the conservative forces. Energy, work is force times distance. Dissipation, well, dissipation is a rate, so it's more like a power, so it's going to be a variation of the dissipation with respect to the change in your spatial domain. So velocity, you can think of it that way, will give you your dissipated forces. And you calculate this and using variational calculus. So a little bit more specifically, but not too much. To get the conservative forces, you do what's known as the principle of least action principle, or stationary action principle, where you compute this quantity called the action, which is kind of like a competition between the kinetic energy and the potential energy integrated over your time frame. And you do a variation of that with respect to the domain that should be zero, and that will yield your conservative forces when you do this process. Same thing for the dissipative force. You have this notion called maximum dissipation principle, developed by Onsager in the 20s, where you do the same thing. You do a variation with respect to a rate now. So the velocity, set that equal to zero, and you will get a dissipative force. And of course, this is going to depend on your system, so you can't write this in some generic way that sum of all the forces are zero, and that's how you get your PDE. But if the PDE is a result of the energy law, then when I go to model this on the computer, it should also have some inherent discrete energy law that I should satisfy, because that's really what's driving everything. And you want to make sure you conserve all the quantities that you want to. And so the energy laws should give you an insight onto what the correct numerical model is. And that was the philosophy we were trying to take when we came up with algorithms to solve certain physical applications. And when I was a grad student working on my thesis, didn't take this approach. I had the PDE, and we had some of the best methods for solving PDEs that looked like this. We took those, applied it, proved that it was well posed to work on this, and we solved the problems, and it seemed to work well. Now we're going to go step back and say, did what we do actually conserve energy and conserve the physical properties? Because things don't work quite right when you do them on a computer. And why? What's going on? This allows you to actually figure out maybe what's going on. So let's pick one problem, complex fluid problem. And in even more specifically, two-phase fluids. So you have one fluid inside another fluid. And a standard approach to doing this is you have what's called the sharp interface model. You take one fluid, you solve those equations using Navier-Stokes to solve those fluids in that region, and solve Navier-Stokes of the other fluid in the other region, and then you couple them together by some interface force somehow. Different way to do it is with a diffusive interface model, and in this case, I let that interface be a little bit malleable. So I come up with this labeling function phi, where in a two-phase you have, if you're in fluid 1, phi is 1, if you're in fluid 2, phi is -1, and then if you're in the mixing region, it could vary between -1 and 1. If you have more fluids, you can come up with more labeling functions and get more complicated. So now let's look at the energy laws that would describe something like this. And depending on the properties of the fluid you're looking at, what you want, you can change this around a little bit, but basically you have change in conserved energy equals the dissipation. Conserved energy is made up of the kinetic energy, so rho here is your mass density. It's going to depend on which fluid you're on, right? Times the speed of the fluid. And then some internal energy, some potential energy. Could be from elasticity, we'll see later, it could come from magnetic fields, but it's some internal energy. And then you have your dissipation. Your dissipation can come from viscosity. We know that the more viscous you are, the more diffusive you can be. So that's where this term comes from. This mu is the viscosity of your fluid. Again, depends on which one you're in. And then some other dissipation that comes from the interface force. And we can model that in different ways. And these parameters basically tell you how thick the mixing region is and how diffusive or and it's oil and water is different than other things. So let's look at this internal energy a little bit more closely. We're going to use mixing energy called the Ginsburg-Landau energy, which basically relates the tendency of the fluid to want to mix together versus stay apart. So we have the Philic interaction, which is a diffusive kind of force, that wants to mix together, so that's why it's got a gradient here. And then you have the tendency of the fluid to want to be separate, so the phobic interaction, and that's why it's kind of like a step function. It either wants to be 1 or -1. And epsilon represents this competition, and what you can think of it physically in the experiments is kind of the thickness of this mixing region. So the thicker it is, the more you're allowing it to mix. Okay, do the calculus of variations on that, and skip all those steps, and you get a PDE system. So you get eventually Navier-Stokes. This is Navier-Stokes equations, use the fluid velocity, P is the fluid pressure, viscosity, mu. But it's going to interact with this interface force, and this interface is going to get advected around depending on the properties of the fluid. So you have this extra force equation, which is the change in the interface, or the labeling function, sorry. And so you have a force up here in Navier-Stokes that's basically the force of the interface acting on the fluid, but we know that any force that acts on something, that thing's going to push back equally and oppositely. So you have a force of the fluid acting on the interface itself. So these interchange. And then there's some nonlinear terms based on the thickness and the parameters of your system. So here's our system. Nonlinear, time-dependent system of equations we'd like to solve. And then you have all these parameters depending on what types of fluids you're looking at, how much you're allowing the things to mix and things like that. And we'd like to solve this. So the first thing we did was the naive thing. We had this solution algorithm that worked for other problems. I'll explain why we use it on this in a second, but we applied it to it. So I don't know if you're familiar with this finite element method, adaptive finite element method. So basically I chop up my domain into little regions, and I approximate my solutions in those regions with simple basis elements. And what I can make this efficient by saying I know nothing's going on up here, so I can have a big space, whereas down here lots of stuff are going on, so you can see these little elements are really, really tiny, because I have to resolve it a lot better over there. So this is a sample problem. I got one fluid, red, and another fluid, blue, 2 bubbles of the blue, and it's called an osculating problem. You guys know what osculating means? Osculating in the back. Anyway, so it's just barely touching, and you set this up. I set up all the parameters so that this thing wants to go together and be one bubble. And we set this up, and it's not going to work at first. So I approve it. And eventually, this thing does what it's supposed to. This bubble starts merging together and becoming one bubble. And it's a diffusive, we set it up to be a diffusive process, so this bubble will eventually disappear, which is not really physical, but for the parameters we set up, that's what happened. This is just a zoom in when I'm talking about the adaptivity. You can see, again, it's really resolved, the algorithm used really resolves itself around the interesting parts and not so much on the other. This allows me to make it more efficient. So I'm not wasting time solving a problem up here when nothing's going on. I'm spending most of my computations down in this region. Okay, so let's look. So we had an energy law for that, but that was a continuous one, so I have to come up with a discrete one that represents this discrete model. And we do, and we look at it, and sure enough, it is dissipative, which is supposed to be. This is a conservative energy. And that dissipation is lined up exactly with what the expected dissipation should be, with this weird blip in here, which we still haven't figured out what that is. In general, it seems to line up pretty well. Try a different problem. Start off with a square bubble. Nature hates squares, so it's going to try to make this into a circle, but it's going to overestimate first, and you're going to get this pretty interesting diamond shape where it kind of over-adjusted and then it kind of backed out, and it kind of oscillates for a while, but the oscillations are really, really small, so you can see it eventually makes itself a circle. This one I changed the parameters a little bit to make it less diffusive, so this bubble lasts a little longer than the other one did. And again, you zoom in, here's when it formed that diamond shape. And in this case, there's a lot of nonlinearity going around, so it actually resolved a lot of it, because it took a lot more work to solve this problem. Again, look at the energy laws, and it's dissipative and it seems to line up in the right way. You guys know why there's that spike in the beginning? Any ideas why that would happen?
Wait, which spike? The one is?
And then it decays.
Is that from the corners?
Yeah, I had to fool my system into allowing for a corner, so this initial condition is discontinuous. And of course, that's not really real at all. So it adjusted itself and then simulation. So I should probably remove that, but then I feel like that's cheating. Okay, so it seems like the method I had randomly made up for this, not randomly, but came up with to solve these kinds of problems, satisfied these energy laws. It looked great. So let's go back and apply it to do the same thing for the thing I did before, which was an MHD, magnetohydrodynamics. So, and by the way, cut me off if I'm going over too. What is MHD? Well, it's a study of plasma physics. Plasmas are all around us. It's a fourth state of matter, so you get solid, add energy, you get liquid, add energy, you get gas, and eventually you add enough energy, it becomes ionized. So it's a charged gas. According to Wikipedia, it makes up 99.9% of the universe, because it's in fluorescent lights, it's in the sun, everything. Particular application I'm looking at is in fusion energy reactors. So here is the...
It makes 99% of what? Of the baryonic matter in the universe? Okay.
That's the headline of Wikipedia. I didn't actually read the article.
It's the fluorescent lights that contribute the...
The fluorescent lighting of the sun. Yeah.
Roughly 80% fluorescent lights.
That's right. Yeah, so I'm going to look at a fusion reactor. So this is the ITER project, International Thermonuclear Experimental Reactor, building in the south of France. It's supposed to go online in the next 10 years for the last 20 years. I've been told 2018 is the target date now, I think. There's a little dude right there, so it's the scale of this thing. So what is this? A torus-shaped object. You're going to put a plasma of hydrogen in there. And if you compress it enough, heat it enough, hopefully the hydrogen starts fusing together. You get fusion energy and it's sustained. How do you do that? There's many ways to do that. In this kind of system, you get really, really strong magnetic fields going around this torus, combine the charged the hydrogen, and make it fuse. And you don't want it to touch the sides because it's really hot, and you have a $10 billion machine, you don't want it to melt. So, lots of things going on there. Therefore, it'd be a good idea if we can simulate this on a computer before you flip the switch on this thing. So what we're going to look at are instabilities that can occur in this system. But how do you model a plasma? Well, there's a hierarchy of models. If you ask a physicist what the exact model of a plasma is, they will tell you kinetic theory, and because you can't model every particle moving around because there's lots of them. But you take an ensemble average of all the particles, and you treat it as a distribution of particles of different types. So you have electrons and ions, say, if you're on a tube kinetic theory. And you can include collisions, or you can't, or you don't have to. If you do not, it's called the Blasov equation. If you do, it's called the Boltzmann equation. Basically, you get this hyperbolic advection-like equation, where so your distribution depends on each particle has a position in space and a velocity and at a given time. So a 7-dimensional problem for every single type of particle. So this is kind of nasty. So it's affected by its velocity, it's affected by acceleration, which is the Lorentz force in this case, so coming from Maxwell's equations. And you couple this with Maxwell's equations. So this is a nasty, ugly system to solve. People do it and get good results, but what this is going to capture, it's going to capture everything, all sorts of wave scales and everything. Some things I don't care about. If I'm looking at instabilities in a fusion reactor, I don't really care about certain high speed waves and things. So you can simplify this and approximate it. So you basically take, average the quantities of motion. So you take moments of this hyperbolic equation, and you wind up with a 2-fluid system if you had electrons and ions, say. Basically, you have a fluid-like, you treat the plasma as if it was a fluid, but you keep in mind that positive things go this way, negative things go that way when you put it in a magnetic field. MHD goes even one step further and says, you know what, it's just one big blob of fluid. And you have one equation describing the fluid. It's Navier-Stokes again, fluid velocity, fluid pressure, viscosity. But it's in an interact, since it's charged, it has to be affected by Maxwell's equations. So here's the Lorentz force in a different form. J is the current density, B is the magnetic field. We have Faraday's law, Ampere's law, Gauss's law, and then I'm going to assume my fluid's also compressible for whatever reason. Sorry, Gauss's law there. And there's no magnetic monopoles. What I can do to simplify this again is I know there's a relationship between electric field, magnetic fields, and current. And it's known as Ohm's law. So here's a generalized version of Ohm's law in all its glory. Lots of terms have different meanings and things, but again, if we're trying to model some physical behavior, some of these are very, very small and negligible. So we're going to ignore them. And you come up with different flavors of MHD. The simplest to look at model would be ideal MHD, where you assume there's infinite conductivity, so no resistivity. So your electric field is just some U cross product of the magnetic field. You include a finite conductivity or some resistivity in the system, then you get a current flowing, and eta is the resistivity. Then you can go and include other terms to get extended MHD. Hall MHD includes the Hall term, which allows you to keep in mind that electrons should go one way and ions should go the other way. This has more information for that. So it makes a little bit more accurate. And then you can add terms as you like. So there's lots of things about this. One of the open questions in this area is, you want to model this behavior in plasmas, which flavor of MHD will work? You talk to a lot of physicists and they'll laugh at you and say MHD is wrong. Well, it is. I mean, it's an approximation of something. It doesn't get everything. So what do I look at? Well, I want to model this phenomena called magnetic reconnection. And in this idea is you have some configuration of your system of magnetic fields, of field lines. And something happens in the system where the configuration, it doesn't like it. The energy gets too high and it wants to get to a lower energy state. Or the magnetic field lines get pinched. So you get something that's, you have the magnetic field lines crossing like this, and then this thing gets pushed in, which is one of the problems I'm going to show you, and it just doesn't like it, so it's going to break magnetic field lines and reconnect in some nicer configuration that it likes. The question is, it's a real phenomena that happens in fusion reactors. It happens, which would be bad to happen in a fusion reactor. It happens in the atmosphere all the time with solar flares and things like that. Can you model it with MHD? And if so, which form of MHD can you model it with? It seems to be concluded at this point that ideal is not good enough. You need some resistivity for this phenomenon to occur. It's starting to look like you need more on that. You need the Hall term that I showed you before also. But we're going to attempt to do it with resistive MHD just because the equations work out nicely. So if you do a non-dimensionalization of all those equations I showed you, you come up with this thing. Again, nonlinear system of PDEs. Navier-Stokes, Maxwell's equations, written in a slightly different form. What you have here is this, again, equal and opposite forces. You have the Lorentz force, magnetic field acting on the fluid. The fluid's going to push back on the magnetic field. No, that's what this vector force here would represent. Okay, doesn't matter. But then we also have these incompressibility or solenoidal constraints. Divergence of the magnetic field is 0. So there's no magnetic monopoles. We're going to assume my fluid doesn't compress, so it's incompressible, so divergence to U is also 0. Why did I think that I could do the same approach on MHD that I could do with that two-phase flow? Well, I'm going to rewrite the MHD again in a slightly different way using some just Wikipedia's vector identity page. And you can rewrite it like this. Well, alright, real quick, change B to grad phi, and it's almost the same thing. At least these forces here are pretty similar. The nonlinearity is a little different. That's because it's a different force. It's an interface force versus magnetic field. But the principal terms in these equations are almost identical. So mathematically, they're very similar, and therefore in the discrete model, the approaches should be very similar. And it turned out they were. So we did the same numerical methods on this. Again, now we want to go back and say, what is the energy law? Is it working? So if you compute the energy law for the MHD system, again, I won't go into it, but it looks like this. Kinetic energy. Now your magnetic field contributes to your internal energy. Magnetic field actually acts like an elastic energy. Like you get an elastic medium, kind of acts in the same way. You have dissipation from viscosity, and you have dissipation from resistivity. This parameter here represents resistivity. This represents viscosity. You can think of it that way. 1 over that. And so there's your system, your energy system. Okay, let's see how it works. So we're going to try to model this magnetic reconnection phenomenon. So we're modeling this tokamak. It's called tokamak, which means torus. And you have this thing, but you're going to assume, this is where it gets real fun, you're going to assume that the outer radius here is so much bigger than that inner radius that we're going to represent this thing just as a straight cylinder. Then I'm going to say, you know what, the magnetic field going around this torus is so strong that nothing happens in that direction. It only happens in this direction here. And then I'm going to say, you know what, I'm only going to look at a thin little annulus in there. Then I'm going to cut that, and I'm going to get a square. And it actually works quite well. This guy came up with this in the 70s, Strauss, that this reduced 2D model of this 3D configuration is pretty close. Of course, we could do better than that, but let's test this out first. Can't do the simple problem, or can't do the hard thing. Okay, so what do we want to do? We start off with some current density, some configuration of my system. What we're looking at here is the current density. 2 islands in the current density. So almost like the 2 circles in the phase field model, the 2-phase model. And we're going to set it up in such a way that we're going to give it a kick, we're going to perturb it, and these 2 islands are going to come together. And what's going to happen is the magnetic field lines are coming through here, like I drew in that picture, and then they start to pinch, they're not going to like it. And a reconnection is going to occur, so the magnetic field lines change, and what that does is cause this spike in current density. That's going to happen right in the middle here. And this is these numbers represent it's the opposite, it's inverse of viscosity and resistivity. So a small number means high viscosity, high resistivity, which makes things easier to simulate actually. And so what's going to happen is the region is going to be a little bit thicker, the spike's not going to be as high, things like that. And another phenomenon that's going to happen is this thing's going to come together, and then it's going to try to push back, and then it's going to oscillate until eventually it just merges into one after the reconnection disappears. So, whoops. Do this and you'll see this happening. And again, there's the finite element stuff. You can see the different sizes of the resolution. So you get this nice peak. It kind of relaxes a little bit and then comes back in, and then eventually this thing just becomes one island, and then this peak will disappear. Gone. Okay, pretty cool, right? Looks like everything's working. Now, what happens, what's more interesting is that when you decrease the viscosity and decrease the resistivity, it makes the problem harder.
50,001.
Yeah. Is there a reason for the one?
Yeah. And many months was spent on this. If you plug in 50,000, the code breaks. And nobody knows what. 49,999 works, 50,001 works. 50,000 does not. Somewhere in there, somebody has this line that says, if 50,000, do something else. Haven't figured it out yet, and nobody, yeah. The code was written a long time ago. Anyway, so roughly 50,000. So the problem's going to harden. What's going to happen is this peak gets smaller and thinner, so the gradients in here are going to get sharper, making this problem a little bit harder. And so we'll apply this. And you get more oscillations to this, what's called a sloshing effect, where these things pass. So everything looks like it's going great, beautiful, and then, splits, and then all of a sudden disaster happens. And so you get this result, you spend a few months thinking you've discovered something really new, and you take it to a conference, and then a physicist tells you, no, it's numerical error. Well, obviously all this stuff is numerical error, but what happened in that peak splitting off? That's the interesting. Why did that happen? Well, now we have a tool to see what's going on. We're trying to validate this, right? Let's look at the energy wall. Conserving energy decreases. It's supposed to. Good. How is it compared to the dissipation? Well, it's a little ugly. It's really oscillatory. It matches up until this is where the reconnection occurred. And you can see there's a gap. I mean, it's 10 to minus 3, but relative to what? So it's a significant gap. Where's that coming from? Well, let's go. Why did I do that? Okay, so there's a problem. Why didn't we see it in the two-phase flow model? Well, it's because I did simple problems. Let's do a harder one. What I have here is a fluid and a bubble. Now I have this weird shaped bubble. It doesn't like shapes like this. It's singularity. And I have a much higher viscosity here. So actually setting this up so that it should act like a solid inside this thing. And so this shape shouldn't change. And it's okay, but notice the edges are starting to get blurred, rounding it off, and it's starting to fade away. And eventually, if you go for a long time, this thing is going to turn into a hideous blob that is not what it's supposed to be. It's supposed to stay this shape with the parameters given in this problem. Let's add some flow into this thing. So this thing should just rotate around, not do anything. Do that, and it starts rotating, but notice it also starts getting diffused and ripped apart, and eventually it should rotate all the way around, and it doesn't. It just starts getting pulled apart like that. Something's wrong. Any ideas?
Nature of porous corners.
Oh, that's true. That is very true.
Isn't it the incompressibility?
Yeah. And the corner thing, actually, both of those things. And numerically, I'm not capturing that. So let's go back to the energy law for the MHD system. It's a similar concept for the complex fluids. Here it was. Notice, maybe, what you'll note if you do this analysis is that the Lorentz force and the advection force in Faraday's law do not contribute to the energy. The reason is because they cancel each other out. They're equal and opposite forces, so they balance each other. So they shouldn't contribute to the energy. Well, this equals this in an energy in this integral only if divergence of u is 0 and divergence of b equals 0. I can't do that on the computer. I can get it pretty close, but I can't get it to be exactly 0. You can't get many things to be exactly 0 on a computer. But in particular, I can't get these things exact enough so that when it feeds back into the other equations, it throws everything off. And it's messing up. And that's why what's happening, and so in that MHT simulation, that split is coming, what's happening is, since I'm not getting this correctly, what I'm doing is introducing this extra instability, a numerical one, which is putting in there, so there's the islands in this direction. Well, what this instability does, it makes another island in this one, and it splits it off there. And as soon as that happens, everything gets messed up, and then it's just chaos. So that's not that meaningful. So it is somewhat meaningful that, you learn something about the physical model that if you don't have this, you get a different phenomenon, obviously. And so you have to come up with ways to get this better. And that's one of the areas of research that we're looking into. How do you use the numerical methods that we came up with? How do you make them better for these types of constraints without ruining how well the other equations are being solved? Because the other equations are being solved pretty decently. I'm getting qualitatively pictures that are looking correct. So basically that's one area I'm looking at. Just to conclude from all of this, so you need advanced techniques in scientific computing to solve these. They're nonlinear, they're time dependent, there are multiple scales going on, a lot of stuff's going on. You need a lot of tools to resolve this accurately and efficiently. You want to do this with minimal work, so it doesn't take centuries to solve the problem. And you want to, again, capture the relevant physics. But the methods, you have to be consistent, so they have to be true to the physical model, the mathematical model. But in the end, they do give you insights into what's going on. And we've learned that these two constraints are important. One question to ask, is it really reasonable to assume that your plasma is incompressible? We know divergence of V has to be 0 because that's a physical law, maybe. But yeah, that seems to be a physical law. But divergence of U being 0, that's not necessarily realistic. Should we even enforce that at all? And of course, you can lead to greater progress in these things. Like it could help out for the ITER project and things like that. And it's just a great way you can apply lots of mathematical theory to these real-world applications. So it's kind of nice to get involved in these kinds of projects. So what do I plan to do? Well, I remember I showed you all these different things. Well, in physical models, there's lots of things to look at. Other complex fluids, multiple phases, not just two, liquid crystal problems, looking at a lot of electromagnetic problems that I'm starting to look at, magnetoelasticity and things like that, and geological processes. Anything that requires simulation to be advanced is I'm interested in. Mathematical models, there's a lot to do, a lot of PDE analysis, energetic variational approach. How do I know that my discrete model actually has an energy law, and how do I know that energy law actually has anything to do with the real continuous energy law? You have to make sure that's clear. And basically how well does it approximate the real physical system. Discrete models, again, that's the main research focus. Develop all these numerical algorithms. There's finite elements. One of the issues with getting divergence-free stuff in finite elements is how do you get a function? So you're representing a function in this little square. Basically, you come up with basis elements for this domain of this square. How do you get those basis elements to be divergence-free and yet still approximate the solution? It's not that straightforward. And then you have issues when you have singularities, like weird corners. Can these functions actually approximate the real thing? So there's a lot of things to look at for there. Solution algorithms, again, you want good linear systems. Actually, that's the worst thing in this whole numerical method was the linear solver. It was really slow, even though it's supposed to be ideal, these multi-grid methods. You have to design them for your specific problem in order to get things right. Again, there's lots of software implementation. You're going to use packages or libraries, or you're going to code it yourself. Parallel computing is important, especially for simulations that big. And then, of course, now we have new architectures all over the place, like GPUs, which maybe are the future, maybe they're not. But you'd like to be able to simulate your things on these things, if you can. And then, of course, visualization, verification, validation. You got an answer. So what? How do you tell everybody that it looks good, right? Or it's the right thing. I showed you movies, but that doesn't really mean anything, right? Who knows what my error norm is, you know? If you can get a real experiment to back it up, that would be great. If I could actually have a little fusion reactor here and compare it, that would be really awesome, but sometimes we can't do that. So mathematics is important, and you can use it for a lot of projects, of course. So that's it. How did I do?
You're fine.
Okay.
Any questions?
What's your favorite math book?
My favorite math book? Wow. I was not ready for that question. You know what one math book said to the other math book?
What?
You think you got problems? Is that a good non-answer?
Are you currently interested in taking graduate students?
I am. Always interested. So if you're interested, or not even working directly with me, just to talk about these problems or anything, I'm happy to meet with anybody and talk about this stuff. Or other areas that maybe you think we could discuss, right? This is a collegiate academic environment. We're all colleagues sharing ideas, right? That's the idea. At least that's my philosophy.
Any other questions? All right, let's thank our speaker again.